Since man invented the water wheel, falling water has always been the greenest source of energy for electrical generation. Almost everything about hydropower is green, and when the turbine bearings are water lubricated, it's even greener. Today, there is a much greater sensitivity to the environmental consequences of oil pollution, and so no release to water is the objective of all environmentally conscious hydro generators. The oil-lubricated main guide bearing on this machine has not normally been a source of concern for leakage. The oil is intended to be contained by a shaft seal below the bearing, and the oil is recirculated. However, there can be no guarantees that a spill will not occur should the system fail. Oil leaking from the bearing could travel down the shaft, past the packing gland, and enter the turbine's discharge or tail water. With grease-lubricated bearings, some losses are inevitable. And grease is replenished on a regular basis, sometimes using automated systems. The Francis-type turbine in this powerhouse transforms the potential energy of fresh water from a snow melt-fed mountain lake into electrical energy. The two-powerhouse project is located in the western United States. This turbine generator unit was built in 1915 by the Pelton Water Wheel Company of San Francisco. It operates with a head of 344 feet and a water flow of 210 cubic feet per second, generating 4,125 kVA of energy. The runner, or turbine wheel, has a diameter of 5 feet 3 inches, and the main shaft is 11 inches in diameter at the guide bearing. The senior mechanical engineer for the Conversión project describes the unit's interesting history.
This unit behind me was originally installed at a different location prior to 1920. It was installed in the alternate location up the hill. It was in service for about 5 years, and in the mid-1920s, the unit was moved down to this location when this powerhouse was built. This is actually a second-hand unit that changed hands in the 1920s. It's run ever since. You can see some of the decoration on the ladder going up to the exciter deck. It's still original brass, bronze, hand railings on it. Very old stuff, so very unique.
The lower main guide bearing ensures that the shaft supporting the turbine below runs true, and positions the runner in the center of the scroll case. The second oil-lubricated guide bearing is typically located within the thrust bearing assembly, above the generator, and poses little risk of leakage beyond the powerhouse. This newly designed and fabricated steel lower bearing carrier will fit exactly into place above the existing turbine head cover, thus replacing the original cast iron and white metal bearing. For several reasons, it's usually better to start from scratch than to attempt to modify and reuse a 100-year-old casting. All critical points are being checked with the Ferro Arm coordinate measuring machine, with reference to the electronic drawing and accurate to within 0.0008 inches. The carrier has now been painted, and the polymer bearing test-fitted with uniquely designed bronze keys, which provide the necessary support and anti-rotation forces. The conversion plan involves removing this bearing and oil pump assembly mounted above the turbine head cover. The existing white metal bearing is contained in a cast iron carrier. This gear pump is the one that serves to supply oil to the lower bearing. Oil flows downward through the bearing, past the slinger ring, and into a containment area of the head cover, where it is conducted by this pipe back up to the pump above the bearing. In addition to this shaft-driven gear pump, there are 2 additional external electrically driven oil pumps that will continue to supply oil to the upper guide bearing and main thrust bearing located at the generator level, but not to the converted lower guide bearing. Below the main guide bearing, this stuffing box was packed with 5 rings of braided packing and a lantern ring. The role of the packing was to prevent any oil from leaking downward and to keep water from entering the powerhouse. The packing runs against a replaceable shaft sleeve. By changing the bearing from oil to one where the lubrication for both bearing and seal is provided by water, the risk of oil leakage is reduced to 0. Additionally, the need to maintain a separate oil lubrication system is eliminated. The water-lubricated bearing is made in 2 replaceable halves. A split and tapered bronze key set is used to lock the bearing in place and permits quick and easy inspection or replacement with no major disassembly. The water-lubricated conversion design uses filtered water to lubricate both bearing and seal. In this view, we see a 2-row segmented polymer seal positioned above the bearing. Below the seal are 2 ports for injection of the pressurized filtered water. This water flows down through the bearing and also up through the seal. With everything measured and inspected, the bearing and seal package is crated and made ready for its trip to the mountains. The terrain in this rugged and remote location demands an unconventional delivery. Helicopter transport is just about the only way to get things done. Wind and weather dictate the available window for this delicate operation. A split shaft sleeve in way of the bearing and seal has been fitted. Welded together in situ, it has also been mechanically secured to the main shaft with a key. Water for the lower main guide bearing is supplied under pressure by a filtration package, as we see here. Another clean water supply option is this self-contained water quality package built by the bearing and seal supplier. It operates on a different principle, using a hydrocyclone to separate abrasive particles greater than 80 microns from the water. This one has 2 separators and pumps for redundancy. In this view of a larger, previously converted turbine, you can see the seal water basin on the top, catching the water leaking past the seal and delivering it downward through the copper pipe on the left, and into the integral discharge duct leading to the low-pressure area above the runner. In other turbines, the bearing discharge may have to be piped away rather than this convenient method of disposal. This panel, built on a slate base, has been in use since the 1920s.
Yeah, adjustable resistor. They don't use those anymore, but we still use them here. On this particular unit. This equipment will be replaced in the near future. In fact, there's a project to replace it, but it's been here since the mid-1920s. This is a new annunciator, which we just bought. It's going to be part of the cabinet. This particular powerhouse had no local annunciator. It was controlled from a different powerhouse.
It has been discovered with careful measurement that once the original lower bearing and carrier have been removed and replaced with the new carrier, the shaft suspended from the thrust bearing above is not located exactly through the center of the bearing bore. Will this present a problem? Or will the electromagnetic forces of operation shift it again to a new and more acceptable locus? A decision is needed. It has been decided that with the bearing halves fitted and gaps measured, a parallel relationship exists between shaft and bearing, and that the bearing can and will safely carry the anticipated side loading. The day for startup has arrived and people have confidence, knowing that this is their second almost identical conversion. Yet, things could still go wrong. First, the water supply valve to the filter tapped from the now flooded penstock is carefully opened. The inlet valve to the filter is next opened. Through the sight glass, water is seen to now be flowing to the lower bearing. Pressure and flow are both required, and here we see that flow reaches the required volume of 2 gallons per minute per inch of shaft diameter. For this unit, approximately 20 to 24 gallons of water per minute are needed. Finally, a visual check is made of the water collection basin to ensure that water is flowing through the bearing's seal elements. Engineers and turbine operators have always been concerned about the risk of wiping a metallic or rubber-type bearing due to loading or lack of lubrication. And destroying a bearing on startup is something no one wants to face. Water-lubricated, high-modulus elastomer bearings, however, tend to be more tolerant of a marginally lubricated start than the higher-friction rubber bearings sometimes used. The operators are anxiously awaiting the start. This is the moment of truth. Slowly at first, but growing in speed, the runner rotates the shaft, which in turn causes the massive generator rotor to turn inside the stator coils. There is no power generated yet because the field has not been energized by the excitation system. Once the shaft reaches the synchronous speed of 300 revolutions per minute, the operator, with an eye on the synchroscope, will apply power from the exciter to the field coils, energizing the windings and beginning the process of making electric power. The water is doing what it's supposed to do: generate renewable electrical energy. And the operators and engineers are pleased. Everything is operating according to plan. These projects, intended to eliminate environmental risk, are handled with professional competence. This relatively small project, with its successful outcome, is typical and demonstrates a sincere dedication to protecting the environment. Not out of concern for potential violations, but because of a basic caring for nature, a caring for their employees and residents of the region. The environment is important to all of us, and this small but meaningful change to operating this piece of machinery can really help to protect the waterway for all to enjoy and benefit from. Forward-thinking utilities have increased peace of mind, knowing that the potential effects of a polluting discharge has been eliminated.